Okay, welcome back, AP Stats, to Unit 2, Packet 5, the last packet in this unit. Woohoo! All right, so before we get started on the packet, I wanted to do a brief review on residual plots. I know that there might have been some lingering questions because I rushed through the end of the last packet, so I want to spend some time making sure we have a good understanding of what residual plots tell us. So basically what residual plots can tell us is whether or not a linear model is appropriate. So with a form of a scatter plot, remember when we talked about scatter plots and describing them? We talked about direction, positive or negative. We talked about strength, right? That's our correlation, weak, positive, weak, moderate, and strong. And then we talked about form, and we said that would be linear or nonlinear, right? So if you think about other nonlinear functions, you can think about quadratic functions, exponential functions, those different functions that you studied either in pre-calculus or algebra. So we could have a different model for predicting data that might not necessarily be a line, right? So residual plots help tell us whether a linear model, a line, is appropriate, or if a different model would be more appropriate. So based on how the residual plot looks, we can say that our linear model is either appropriate or not appropriate. So I've got some residual plots for you, and I want you to try and answer whether or not you think a linear model is appropriate or not appropriate when I show you the plot. All right, and to answer whether or not the model is appropriate, I'll give you a quick visual cue. So if your model is appropriate, I'm going to show you this. If your model is inappropriate, you'll get this picture. All right, here we go. Give you a second. Okay, I hope you said inappropriate. So this model is inappropriate because you can see that this residual plot is not random, right? So do you see how we have a curved pattern here? We have negative and then positive and then negative. That means our data is likely curved and that a line would not be the best model for this specific data. So remember, residual plots always have our x value, right? Our explanatory on the bottom, and then our residuals on the y. So everything above this line is a positive residual, and everything below the line is negative. Remember, our residual formula is actual minus predicted. So you can have a positive or negative, right? Okay, I'll give you a minute for this one. All right, I hope you said appropriate. So this is appropriate because it looks random, right? And also about 50% of the data is on the top and 50% is on the bottom. So that means I have about the same amount of positive and negative residuals, meaning that my line goes straight through this scatter plot and that my scatter plot data has a linear form. So each dot, remember here, represents the residual, and the residual is actual minus predicted. All right, let's try this one. I'll give you a minute. All right, I hope you said inappropriate. So you see this curved pattern in the residual plot, right? It goes from negative to positive and then negative. That's not random, that's a pattern. And that means that our linear form is just not the best form for this data. All right, here. Appropriate. So you've got, again, about 50% of the data above and 50% below. And then it looks like a random, there's no specific pattern of positive, negative, or anything like that. So our linear model is appropriate. It goes right through the middle of the data. Okay, this one I tried to trick you with. So with this one, I would say that we can determine two things based on this residual plot. So we can, one, determine that a linear model is probably pretty appropriate because I've got kind of a random pattern, right, with half of them above and half of them below. But here's the catch. As I go further down the x-axis, my residuals start getting bigger. They start fanning out. So what can we say from that? As our explanatory variable goes up, our predictions are not as accurate. So do you see our residuals are basically how far our predicted values were off from our actual, and they get bigger as the x value goes up. So it would look something like this. Do you see how on the lower x values, all of our dots are close to this line, right? But as we go out and the x values go up, our predictions get further and further away. So that means we can probably only use this line for a certain range of x, right? And then after that, our predictions are just getting crazier and crazier. So that's what this fanning out looks like. All right, nice job, and we can answer any questions about these in class on Monday and Tuesday. All right, let's get to the packet. All right, Unit 2, Packet 5, Standard Deviation of Residuals and R-squared. Our learning objective, interpret the standard deviation of the residuals and R-squared and use these values to assess how well an LSRL models the relationship between two variables. And number one, when we're talking about variables, we're obviously talking about quantitative variables, right? Because we can only put numbers into our least squared regression line. All right, so number one, how do we know if our LSRL is a good predictor of a y value when we have a given x? So think about something. I've got a model, right? I've got an equation, and I plug in an x value to predict how my y value is going to be. How do we know if it was a good prediction or not? We compare it to the actual, right? So when we've compared it to the actual, and we see how far away from the real number it is, that's how we calculate a residual, right? Remember, our residual is our actual y minus our predicted y. So if we have a good model, a good LSRL or model, right, will minimize residuals. If residuals are errors, are prediction errors, right, then a good model will make those errors as small as possible. Do you think there's a way to estimate a typical prediction error when given an LSRL? So I could say that my equation is usually this much off, right? And there is a way to do that, and we do that with the standard deviation of residuals. So that's what we're going to talk about first. All right, so number one, vocabulary. Standard of deviation of residuals. So we use S to signify standard deviation of residuals. So what that does is it measures the size of a typical residual. And I'm just going to put the word error right here so we can always know what we're talking about when we say residual. We're talking about error, right? How off, or I should say prediction error. How far off our prediction was from our actual, right? It measures the typical distance between the actual and the predicted. So the actual y context is typically about s units away from the y context predicted by the LSRL. And I'm going to add something right here. With x equals the explanatory variable. All right, and I know this doesn't make a lot of sense, so let's try an example. All right, example 1. Desiree is interested to see if students who consume more caffeine tend to study more as well. All right, so just think about that in your head. We're trying to see if students who have more caffeine study more as well. So we know that our explanatory our x value is going to be caffeine intake. And what's our unit? We need to always write our unit. Milligrams. And our response is going to be number of hours studied. All right. So she randomly selects 20 students. So that number 20 is our N. N just means the number of people in the study or the survey. So if you ever see N, it just means number of data points in like the scatter plot or in the study or anything like that. All right, a scatter plot of the data showed a linear relationship. That's good. So I can use our linear model. The least squares regression line with the variables is defined below. Y hat, or our predicted value of y, is 2.544 plus 0.164x. where X represents caffeine intake and Y represents hours spent studying. Perfect. We already said that over here, right? So let's take a minute and see if we can interpret the slope and the y-intercept. You don't need to write anything down on this. I just want to make sure that we have the most practice with this since we've already gone over it. So first, let's interpret the slope. So remember, our slope interpretation is for every 1 unit increase in X, our predicted Y value goes up by the slope, right? So let's think about what X is. Caffeine intake in milligrams. So for every 1 milligram increase in caffeine, the predicted number of hours studied will increase by 0.164 hours. And I said increase because the slope is positive. All right, and then our y-intercept. Does it have any sort of meaning in this scenario? So with the y-intercept is always X is 0, right? So think about what it would mean for X to be 0. X, caffeine intake. Can we have no caffeine and still study? Yes, we most certainly can. I wouldn't recommend it, but you can do that. So if caffeine intake is 0, our predicted hours of studying is 2.544 hours. So yes, the y-intercept does have meaning in this context. All right, now back to the actual packet information. Our S, our standard deviation of residuals, our typical prediction error. Typical prediction error. All right, so S equals 1.53. 1.53 what? Does S have units? Let's think about this. If we have a typical prediction error, that means we were off predicting, we had a mistake in predicting something, right? We either overestimated or underestimated. So we overestimated or underestimated what? What are we trying to predict? What's our response variable? Here, hours studied. So if we were off in predicting and we were off by this much, we had to be off predicting hours, right? So our unit for S, and I want you to write this back up here. Your unit is always going to be your response variable unit. So anytime you see S, I want you to put the response variable unit right after that, hours. All right, so now here we're going to actually interpret this value. So our prediction error, we're going to use our sentence stem up here, right? The actual hours, because our Y context is hours studied, right? The actual hours studied is typically about 1.532 hours away from the hours predicted by the least squared regression line with X equals caffeine intake in milligrams. All right, beautiful work by me. All right, now the word that's important that I want to talk about here is the word away. So the actual hours studied is typically about 1.532 hours away from what was predicted by our model. So does that mean above, below? Could it mean both? We never want to say above or below when we're interpreting the standard deviation because the standard deviation could be above or below, right? We just know we're about 1.5 hours off. We don't know which way. It could be either way. This is just about our normal prediction error. I could have predicted 1.5 hours above what actually happened, or I could have predicted 1.5 hours below what actually happened. So that's why we just use this word away instead of above or below. All right, flip it over. I want you to go ahead and try example 2 on your own. So go ahead and try this on your own, and we'll go over it in the next video.